Okay, next demo. Something different, but not completely. We're still in sort of boundary velocity domain, but very different environment than the recording studio we just visited. So this is a car cabin, and the initial geometry was obtained through a LiDAR scan, thanks to a very good collaboration with our friends at Audio. So thank you very much for that and the good collaboration. We did a scan of this car and then imported that LiDAR scan into a CAD tool for further processing, sort of putting in some more details and using the LiDAR scan as a sort of as a background to essentially make the car model from. And then that car model can then be uploaded into Treble to perform an acoustic simulation on. So what we're going to do here is sort of modeling an infotainment system in a car, so a multi-way speaker system. We're going to do a 1 kHz simulation of the woofer in the trunk, and then a spatial receiver in the driver's seat. And we're going to do that fully wave-based up to 1 kHz. And then we're going to do a KEMA rendering as we did before for oralization purposes. And this time the filtering will be done with a TIL small parameter model, lump parameter model. So we are going to do like create a physically informed filter here. And then we're going to do an 8 kHz simulation of a tweeter pair situated in the car doors. Also with the spatial receiver obviously in the same position at the front seat. And this 8K simulation will also be fully wave-based. We're going to get some spatial responses from that. We will render it with an HHF of the KEMA mannequin again, and then the tweeter response will be made from a lump parameter model here as well. We'll combine them and then do a nice oralization at the end. So for the tweeter pair, let's first log into the SDK and fetch the car cabin project here. We're going to quickly import the 3D model of a car into Treble. That was fast. Look at this model, quite complex actually, and it's right here. I'm impressed every time. Sorry about that, but this is just really cool with the level of detail you can do in the software. Out here on the right, we see it's a very complex model. We have a lot of different layers that we have to assign materials to. So in the next step, the material assignment function is very condensed. So we use a config file actually here for the material assignment that's hidden away, but of course available with the notebook. Just gonna run this here. And then we are gonna load a tweeter submodel. So this time we're just gonna interact directly with this boundary velocity submodel library. Gonna query for the speaker name, and we have our tweeter. No further things are needed. We can just directly use that in the source list to make a boundary velocity source in the car doors, and then we're placing the receiver in the listening position in the driver's seat. So that's basically it. And then we will create a simulation definition with a crossover frequency or like an upper frequency limit of 8,000 Hertz. So then the simulation model of the car will look like this. We have the tweeters here situated in the doors, left and right, and then we have the listening position here in the driver's seat. 5 blocks of code. You have a car in Treble plus a tweeter pair. Gonna add that simulation to the project, and then we can choose to run it. For the sake of time, I'm not going to, but you have this left-right channel and then this receiver. Computational time of something like this, 8 kHz, very high fidelity, very accurate, and very detailed model. It's 1 hour. You can, one source, one receiver is 1 hour. In this case we have 2, but the simulation time is still 1 hour because we are a cloud company. So we send the simulation to the cloud and we just spin up 2 GPUs instead of 1. And it would be the same if you have 16 loudspeakers in your infotainment system. It will still only take 1 hour to do this car in Treble. we move on, and we also want a big, nice woofer in the trunk of our car. So we query the submodel library for a woofer with a 1 kilohertz simulation. And we can add that to our source list, and that can then be added to the simulation definition. So this is a new simulation we're doing. We're reusing the car model, but now we are injecting a subwoofer into the trunk of the car, right here. And now we're going to compute then the impulse response from the woofer to the spatial receiver in the front. We can add the simulation to the project, and then we can run it with this lines of code. Again, we have already run it, so I'm going to press no here. So yeah, this is basically how you would compute the car cabin acoustics for the infotainment system in the car in Treble. We'll now move on to the post-processing script. So this sort of emulates, okay, the simulation takes an hour, you're going to do something else. I mean, you can just continue your work. This is a cloud simulation. It's not blocking your computer or anything. It just runs in the cloud and you can do something else. So now the simulations have finished. I will log into my account again. We'll load this Kima mannequin from the device library. Again, we have to load the project we just did. We're fetching the simulations, and then we are getting the results object and putting it in this results here. Then we are rendering via the spatial IRs in the loop, giving us the woofer and the left and the right channel, so the tweeter pair, essentially. So far, so good. So last time we did these Butterworth filters to make a crossover network that we could then use for all organizations. Here we're taking it one step further to show how could you use TIL small parameters in post-processing in Treble, electroacoustics. And we actually have two different ways of doing that here. So for the woofer, we use a sort of what we call a generic model. So of course we input the membrane radius of the woofer, but then the resonance frequency, QES, QTS, and the BL factor is all you need to create the lump circuit of the woofer. So that's one way of doing it. Another way is just using directly the TIL small parameters obtained through measurements or data sheets or whatever. So the electrical components here, RE and the BL factor, together with the moving mass, RMS, CMS, and then we also take into account the volume of the box of the tweeters. And then to sort of just visualize how these filters work, we create an impulse response, just some impulse response just to show before we then process the actual car simulations with this signal. So we define a transition frequency for the woofer at 300 Hertz and a gain. And then we do a crossover network again here, so we make a Butterworth filter and that is low pass, and then we make a Butterworth filter that is high pass for the tweeter pair. Then we can go and view the frequency response of this lumped circuit. We see the frequency response here of the woofer, and then the frequency response of the tweeter here. We can then move on and then do the filtering on the device IRs we obtained before from the simulations, using the low pass filtering the woofer to design a crossover network, and high pass filtering the tweeters. But then I think most importantly here is using then this woofer lump parameter model to filter the woofer response. And similarly for the tweeter, we use the tweeter lump parameter model to filter that. And then we plot the combined response. So if this frequency response have quite a bit of information, so I'm just going to first start with the combined response. So I mean we add things together, right? So it's possible to to show basically what will the frequency response in the car be if we use these filters, then it will look like this, and then we can start to sort of investigate the individual components. So what is the woofer contribution to this response? What is one of the tweeters' contributions, and what is the other one? And then you you get this. So you can examine the individual contributions or just look at the combined frequency response, which probably is the most interesting. Then we have a small organization example for this infotainment system. So we start by loading some car noise in, just to give you a sense for that. I'm going to play it back here. Okay, and then we are going to combine the background noise with a song, the Fleetwood Mac song, The Chain, where we're going to assign the mono signal to the subwoofer, and then the left and the right channel to the tweeter pair. Then we can analyze that as well. Okay, so there was an idea of how you could do infotainment system modeling in the Treble SDK, injecting these bound velocity sources in, and then doing left and right channels, and then a subwoofer in the back, using lump parameter models to filter the response. We also have a different example. So one thing is, of course, modeling the infotainment system, but another thing is modeling how a conversation would be in a car. So we have an example of an SGI simulation as well, where we again will use the same car model with the same materials, and here we're going to inject an entire mannequin into the front seat, and then place receivers at the passenger seat location and also in the rear of the car. And the simulation will also be run up to 8 kHz wave-based, of course. And then we're going to look at some acoustic parameters, in this case the speech intelligibility, and analyze that. So again, we're logging into the SDK and fetching the project and so on, and then we are loading the car model in again. It's the exact same model as before. We're going to assign materials in the same manner. And now the difference comes, you can say. So that's in the source modeling. We have a scanned model of a mannequin here, typically used in many different measurement setups in cars, but also communication device modeling and headphone modeling and so on. But here we choose to use it in the car. We have this surface here. You can assign a boundary velocity source to it. So I'm just going to add that to the source list, and then at the same time we are making these 3 mono receivers, 1 in the passenger seat and 2 in the rear. And then we're going to create the simulation definition up to 8 kHz with the car model, and then we're going to plot that here. Five blocks of code, and we can inject the mannequin into the front seat. I think that's really impressive. Then we can use that as a speech source and compute the impulse response functions to the different receiver locations, and use that for the speech intelligibility analysis. So we can quickly add the simulation to the project, and then we can decide if we want to run it or not. In this case, the answer is no. In your case, if you want to try this notebook out yourself, it will of course be yes for the first time. So yeah, now we have a simulation here, and we go into a post-processing step. Here, I'm just gonna again log into the SDK, and then we're going to fetch the project, the simulations and the results, and then we will use this plot acoustic parameters function that you can do in Treble on the results object. And in this case, we're going to do SGI between the speech source from the mannequin and then to different positions in the car. So here, I think it would be very nice to compare how's the experience of the passenger in the front versus a passenger sitting in the rear to the right. Yeah, I think that was it for the car demo. I hope you liked it. I think it's very exciting that you can not only do rooms in the SDK, but you can also upload way more complicated geometries like cars and so on. I'll remind you that you can also check out our documentation that also goes live together with the Treble 2.0 on Tuesday, where there will be plenty of examples and good documentation and guidance how to do these things and much more. Thank you.